Imagine detecting ripples in space-time, not with these kilometer-long instruments, stretched across the landscape, but with something you can maybe hold in your hand, or at least fit on a tabletop.
Yeah, it sounds like science fiction almost.
Right. That's the audacious proposition we're diving into today. We're looking at this really fascinating intersection of theoretical physics, quantum tech, and experimental innovation. And it's all sparked by our conversation with Dr. Barceló.
And our mission for this deep dive really is to unpack this idea. It's potentially paradigm shifting, how quantum sensors, specifically these ultra-cold clouds of atoms, could just fundamentally redefine how we detect gravitational waves.
And maybe even fundamental physics itself.
Exactly. And it's kind of a shortcut, to appreciating how something profoundly small could become profoundly powerful.
Okay, so let's unpack that. Dr. Barceló is proposing something, pretty revolutionary, using Bose-Einstein Condensates, BECs.
Right. These states of matter where atoms basically lose their individuality and act like one single quantum wave. Super weird, super cold.
And using these as incredibly precise gravitational sensors. The scale difference is what gets me. She's talking, 50 to 100 micrometers?
Yeah.
A tiny speck.
Yeah, a tiny speck potentially detecting space-time distortions.
Compared to LIGO, which has arms that are like 3 kilometers long.
Yeah.
It's just mind-boggling.
It is. And why this matters so much for you listening and for science generally. I mean, think about it. Gravitational waves were first found using these enormous multi-billion-dollar facilities.
Totally inaccessible for most researchers.
Pretty much. So if Dr. Barceló's idea works, it could, democratize the whole field. Suddenly the cost barriers, the sheer size barriers, they just plummet.
You could have university labs doing this. Maybe labs that could never have dreamed of it before.
That's the hope. Imagine, a lab somewhere that's usually priced out of this kind of big physics, suddenly contributing to gravitational wave astronomy with a tabletop setup.
Yeah.
That's transformative. Makes cutting-edge science way more accessible.
Okay, so the big question then is how? How do you shrink something from kilometers down to micrometers and still detect these incredibly faint signals? This seems like the core innovation.
It really is. So the standard approach, the traditional way, uses something called atom interferometry.
Right, I've heard of that. You sort of split atoms, let them travel different paths, and then recombine them.
Exactly. You put them in a superposition, let gravity affect their paths slightly differently, and when they recombine, the interference pattern tells you about the gravity they experience.
And the bigger the path difference, or the longer they travel, the more sensitive it is. Hence, the huge detectors or dropping things from towers.
Precisely. You run into limitations based on physical space. How big can you build it? How high can you drop it?
Okay, so that's the old way. What's the new idea?
This is where Dr. Barceló's work gets really, really interesting. She shifts the whole paradigm to something called frequency interferometry.
Frequency. Okay, so not space.
That's spatial paths.
Yeah.
Instead, she's using frequency differences within the quantum states of the atoms themselves.
The core insight, the sort of aha moment, is that the precision here scales with time, not how far the atoms physically move.
Okay. So instead of needing a bigger device, you just need to observe for longer.
That's the essence of it. You could potentially get incredible sensitivity, and even better sensitivity, in a much, much smaller package just by maintaining the quantum state for a longer duration.
Wow. So the engineering challenge completely changes, doesn't it?
Totally. It goes from how big and stable can we build this physical structure to how incredibly well can we isolate this quantum system and keep it coherent for a long time.
Which is still a massive challenge, I imagine.
Oh, absolutely. But it's a different, potentially more scalable challenge. It feels much more aligned with where quantum technology is heading anyway, controlling and maintaining delicate quantum states. It feels revolutionary.
And you mentioned this isn't just for gravity waves. Right. That's a fascinating bonus. Because these sensors would be so exquisitely sensitive to tiny disturbances, they could also potentially pick up signals from elusive things like dark matter or dark energy.
Things that interact very weakly.
Exactly. And there are more immediate practical uses too, like in commercial gravimetry, measuring tiny local variations in gravity for things like geological surveys or navigation.
So this isn't just theoretical pie-in-the-sky stuff. She's actually building things.
Oh, yeah. She's deep into the experimental side. She's collaborating with real pioneers in atom interferometry, people like Chris Westbrook and Philip Boyer. That tells you this is a serious effort to make it work.
Okay, so what does the actual experiment look like? What's this new sensor she's developing?
So the current focus is on using BEC phonons.
Phonons. Like sound waves.
Sort of, yeah. Think of them as quantum sound waves, collective wiggles, basically, within that ultra-cold BEC cloud. Because the BEC is so pristine and cold, we're talking nano-Kelvin temperatures, incredibly cold, these phonons are very stable and precisely controllable. The idea is that these phonons would be exquisitely sensitive to the tiny stretching and squeezing of space-time from a passing gravitational wave.
So the quantum sound wave changes frequency or something.
Exactly. They'd act like tiny, supersensitive resonators. They'd ring or shift in a specific way when a gravitational wave passes through. She calls it a kind of quantum Weber bar.
Weber bar.
Wasn't that an early discredited idea for gravity waves?
It was, yeah. Based on giant metal cylinders. This is like a nod to that history, but using quantum mechanics to achieve potentially vastly greater sensitivity on a microscopic scale.
Okay, that's the experiment. But what about the theory underneath it all? What gives her the confidence that this should even work? You need some framework to predict how these quantum systems will react to gravity, right?
Absolutely. That's critical. You can't just build it and hope. Her work is grounded in quantum field theory applied to curved spacetime.
QFT in curved spacetime.
Okay, that sounds heavy.
It is, but it's not quite a full theory of quantum gravity, the theory of everything. It's more of a very powerful semi-classical approach.
Meaning?
Meaning it takes established quantum field theory, how particles and fields behave, and plugs it into the curved space-time described by Einstein's general relativity. It treats gravity classically, but the matter quantum mechanically.
So it's like a bridge between the two.
Exactly. It's a bridge theory. It lets you make precise calculations about how quantum systems, like these BECs, should behave in a gravitational field like Earth's. And crucially, it gives you the predictive power to actually design these new sensors and know what signals to look for.
So it's doing double duty, pushing fundamental physics questions, while also enabling these practical sensor designs.
Precisely. It's this really neat blend.
It is compelling how she mixes that deep, almost philosophical curiosity,
Yeah.
asking what is reality, fundamentally with this very practical focus on building devices. But what are the big hurdles? I mean, this sounds amazing, but it can't be easy.
No, definitely not easy. The biggest technical challenge, as we touched on, is coherence time. Keeping that delicate quantum state, the BEC and its phonons, stable and isolated from noise for long enough to build up the signal for, say, a faint gravitational wave, that's really hard.
Requires incredible control over temperature, vibrations, magnetic field.
Everything. The engineering is demanding, no question. But even with those challenges, the potential for commercial applications is already there, which is pretty exciting.
Like the gravimeters you mentioned.
Yeah, exactly. Her designs could lead to much better commercial quantum gravimeters. She's actually patented some ideas. Think about civil engineering mapping underground structures, finding resources, or navigation having a gravity-based positioning system that doesn't rely on GPS.
So there are companies already working in this space.
Oh, yes. There are companies like Muquans, for instance, which actually spun out of the research group of one of her collaborators, Philippe Billet. It shows that this kind of research, even while aiming for fundamental discoveries, can lead to real-world products and businesses. The pathway's there.
It's interesting, she describes herself as a contrarian. You can see how that fits, right?
Yep.
Well, everyone's focused on these huge LIGO-scale projects or space missions like LISA.
She's deliberately looking for the compact, elegant, maybe overlooked alternative. She seems to thrive on that tension between, useful science with immediate applications and the pure, fundamental blue sky exploration.
And that contrarian streak seems key to her breakthroughs.
I think so. And what's really neat is how her approach isn't necessarily competing with LIGO or LISA. It's actually complementary.
How so?
Well, her proposed sensors, because of how they work, are naturally tuned to detect higher frequency gravitational waves than LIGO is sensitive to.
Ah, so it's like listening to a different part of the cosmic orchestra.
Exactly. LIGO hears the low bass notes. Maybe her sensors could pick up the higher frequencies. So together, they could paint a much richer, more complete picture of all the gravitational waves washing over us. It expands the spectrum we can observe.
That makes sense. It's not either, it's adding another tool to the toolbox.
Yeah.
So what's next for her then? Where does this go from here?
Well, she's actively working on securing funding for the next experimental phases, really pushing to build and test these phonon-based sensors. She's also continuing fundamental theoretical work, including some fascinating stuff with Roger Penrose on gravity's possible role in quantum mechanics itself, in quantum state collapse.
Wow. Okay. Deep questions there.
Few questions, yeah. So it's really this ongoing cycle. Push the theory, design the experiment, build the device, refine the theory, stepping closer and closer to potentially a unified quantum gravity sensor. It's a fascinating journey to watch.
Definitely.
And if you step back and look at the bigger picture, what this deep dive really highlights is, well, a potential paradigm shift, maybe, both in how we think about detecting gravity waves and how we actually do it.
From massive engineering projects to tabletop quantum control.
Right. It shows how these small-scale, frequency-based quantum devices might soon pull off feats that we thought needed billion-dollar facilities. It shows how really elegant theoretical ideas can spin off into commercially viable tech. And maybe most importantly, how we can tackle these huge questions about the fabric of reality using tools from experimental quantum science.
So as you go about your day-to-day, maybe think about this. These tiny tabletop experiments, humming away in labs, could one day unlock secrets of the cosmos that we assumed required observatories the size of planets.
Hmm.
And maybe consider what that means for who gets to participate in this grand quest for knowledge when the tools become potentially so much more accessible.